Okay, let's start. Are there any questions from yesterday? No questions. Okay, so we started to move from one particle to many particles and see what will happen when we put together these catalytic colloids or phoretic colloids. Because we understand everything about a single one of them, we understand what kind of environment they carry with them, the non-equilibrium activity. We can build up our way and systematically look at how two of them interact and how many of them interact. And this is what we plan to do next. Because when these objects are apolar, when they break the symmetry in the form of a Janus particle, let's say, they will have complicated interactions between the polar aspect and the gradients that are generated. First, I want to focus on fully symmetric but phoretically active colloids. So let's just ignore polarity and think about what the positional degrees of freedom will do when we put together these colloids. And then once we are comfortable with these elements, we will add the polarity at the next step to go deeper into understanding these systems. So let's think about these spherical colloids. We started this yesterday already. So essentially, if we have two different types of these phoretically active colloids, let's say they're catalytically active, this particle 1, has a rate of activity which is alpha 1 and a mobility which is mu 1, and particle 2 will have rate of activity alpha 2 and mobility mu 2. Then each particle will interact because of a 1/r potential which is generated by the other one. So you can think of it as a Coulomb interaction or a gravitational interaction. This plays the role of a potential. And when you multiply it by the mobility and get the drift velocity, it will essentially look like an electric field or a field of gravity, except what sits in front of this very familiar expression will be basically a new notion, which is essentially the charge or the mass that generates a field will be different from the charge or the mass that will respond to the field. And because of that, action-reaction symmetry will be broken, and we start to have fluxes in the system. You can first try not to think about too much and just simulate the system and see what you get. So here is a Langevin or Brownian dynamic simulation setup of these 1/r interacting or 1/r squared interacting in terms of the field particles plus some exclude volume effects, and we took two different types, normalized the charges so that we can think about alpha and mu, well, in this case alpha tilde and mu tilde, as valences. So let's just think about ionic systems and have these particles with different valences. So particle B is basically monovalent, negatively charged in this non-equilibrium sense, and the alpha particle is multivalent and it's the opposite charge. So we expect them to attract each other, and so A and B, we expect them to attract each other, and B and B to avoid each other, and A and A to avoid each other, and this will be largely what will happen, so that we can concentrate on the interaction between A and B molecules. Let's see what happens. So here is a simulation in the case where A has alpha valence 3 and mu valence 0. So they start seeing each other and they start forming these molecules or clusters, but the molecules are asymmetric because the A and B activity are different. So they are exactly the same as a Janus particle. They can self-repel. But there is not just one way to do this. In this case, for the set of parameters that we have here, we can both have AB and AB2. And they seem to be in equilibrium with each other, exchanging B particles between an AB2 and an AB and also in contact with extra B particles that are available in the system. You can look at what happens when you change the parameters. For example, the diffusion coefficient of the colloids playing the role of temperature in this system will essentially control what kind of molecules or structures we get. At very low temperatures, we get really big clusters, and I'll talk about them briefly later on. At relatively higher activity or diffusion or temperature, we tend to have smaller clusters in this region of the parameter space. And the peak of the population essentially changes. So here you have, let's say, AB2 molecules as the predominant form of the molecules. Here you have AB molecules, and then up here you only have monomers left. We check that this is essentially insensitive to the concentration. This is very low volume fractions, and as you change the volume fraction in this range between 10 to the minus 4 and 10 to the minus 3, I think you basically don't see much change in the behavior. So this is essentially the dilute limit behavior. Now, if you think about alphas and mu's as charges, you should be worried about what you're seeing here, because there is no notion of neutrality. So the one thing that we know about electrostatics is when you have basically an atom or an ion of a certain valence and another one of another valence, they team up and form ionic molecules if they neutralize each other. Otherwise, it doesn't work. And here we have deliberately messed with the numbers so that you cannot really tell which one of the valencies is in charge. So the alpha valence is not happy when this is 3 and this is -1. If you form an AB molecule or an AB2 molecule, you would expect an AB3 molecule. But that's probably because the mu valence is also playing a role. And as you can see, here we even set mu to 0 for A. So A is a particle that doesn't respond to the gradient, and it's the B molecules that come and interact. So because we have two different species of charges, this will be a complicated system. And before showing you more movies of more different types of behavior, let's look at what is happening here in more detail. Yes. Yes, so the 1/r interaction essentially as solution of diffusion equation or Poisson equation is the monopole contribution. When they get close to each other, you have to add the other ones. But when you want to deal with, when you want to build an analytical theory of these systems, as you would do with ionic systems, you would start with the monopole, and basically you expect that the description you get will be qualitatively correct, and small changes will happen when you bring in higher multiples, but that's a valid point. Okay. So we had this expression. And we want to describe dynamics of, let's say, these two colloids. Suppose this is my B particle and this is my A particle. So what I'm seeing is this one, let's say we have chosen alpha and mu such that there is attraction between them so that they form these molecules. we are saying that B is experiencing a different drift velocity compared to A. So we're describing them with these two vectors. And then we can say, to understand what happens to a pair like that, maybe we can go to the relative coordinate system and the center of mass, and then look at the relative velocity and the center of mass velocity. And let's also add an interaction potential, let's say U of RB minus RA, so that in case they have other physical interactions, which they do, for example, when they come in very close proximity, there will be exclude volume, then we can account for that as well. So this interaction is going to, I call it equilibrium interaction. By calling the diffusion coefficient of the colloid dc and assuming that they are of the same size, I can write the drift velocity of a particle like that using gradient of u, and then I notice that because this is the equilibrium component, drift velocity of B is exactly minus drift velocity of A. Okay? Right, so we can go from RA and RB to difference. We call it R, and then the center of mass, and then we can work out the corresponding velocities. So the relative velocity will be only a function of the relative coordinates, so that's nice because we can solve it, and then whatever information we get, we can use it to solve for the center of mass velocity. The way the charges are combined here is essentially, so as you noticed, the condition for non-equilibrium behavior is that this relation holds, so I have asymmetry between the products, and this average actually is not sensitive to that, whether that is the case or not, whereas the center of mass velocity is controlled by the difference. And that means when the system is at equilibrium, this will vanish, as you expect. And when it's away from equilibrium, essentially this system will have an overall self-propulsion velocity. So this is a molecule, you can call it an active molecule, which is swimming because of the binding, the sort of generalized ionic binding between these two components. So in simulation, you saw that A and B collapse and basically stay in contact. That's when that happens when the interaction is sufficiently strong to make sure that essentially this will keep them close as compared to, let's say, or in competition with thermal fluctuations, and the interaction that we used was only exclude volume, so to prevent that collapse. You can have more complicated situations. Essentially, the behavior that you will get is going to be statistical. And in particular, we can calculate the probability distribution for the distance between these two. By looking at the stationary behavior, and what we will get looks like looks like an equilibrium behavior. Let's say in an ionic system, you have a 1/r part where you're comparing your generalized energy with something that plays the role of temperature here. It's dc. And then you also have the equilibrium part, which is present. If you know the literature of ionic liquids, you will have heard of Bjerrum length. Which is given by E squared divided by the dielectric constant of the medium and kT. This is a length. It compares essentially electrostatic energy with the thermal energy. If you're talking about ions dissolved in water, let's say epsilon has a number around 80, and then you can put in values. At room temperature, you get something like 7 angstroms. So that tells you that when two ions are closer to one another than 7 angstroms in water at room temperature, they see each other electrostatically very, very strongly. And then when they are farther away than that distance, essentially thermal fluctuations will win. Yes? So I assume stationarity in the relative coordinate. So I set the relative relevant flux to 0, and that gives me a probability distribution for this quantity, because essentially everything in this quantity will be a function of r. So the velocity is given as a function of r, and there will be a diffusive flux, which is also a function of r, and then I solve for the... Okay, so here I can also define a Bjerrum length. It will be a generalized one. I'll call it L. And that's essentially, and I use absolute value. And then I can use this distribution, essentially write it as if I'm assuming attractive interaction between the two colloids, which is this case. So that's very similar to how you look at ionic bindings in liquid. Okay, so we have a distribution for R, and we know what the center of mass velocity is in terms of R, so we can use a Jacobian and turn it into a distribution for the center of mass velocity of this molecule. And when we do that, I really don't want to penetrate that space, so I'll do it. here. So because V is a function of basically V is 1 over r squared, I can use the Jacobian, and then the exponential will come out as square root of V with the velocity scale, which is essentially a function of all these valencies. And if you look at the behavior of this distribution, essentially you only see the power law part, which is the prefactor, and the exponential will have a chance to grow later on, but it won't basically get to do it in practice, because essentially there is a lower limit for the value of r, and that's the radius of the colloid. So it will be cut off by a maximum value for the velocity, which is essentially the value for velocity that you get when you set small r to big R, and that's of the same order of, as you have over there, the quantity called V naught. So V maximum will be of the same order as that, which means the exponential part will be a slowly varying function. Okay, any questions so far? So, yes. Yes, and I'm assuming that it's the same for both A and B, so same radius. So the important point about fluctuations of these colloids is that you always have the thermal fluctuation, which is the equilibrium fluctuation, plus all these corrections that we calculate. And if you put in numbers, so propulsion is different because you're introducing something basically over no prior value, over no bias. So when you get the self-propulsion velocity, that's what you observe. When you get corrections to the diffusion coefficient, let's say, you can introduce that, but then when you look at the numbers, they will be typically small. So in this calculation, I ignored those, and I'm just assuming that the fluctuations, the diffusion coefficient of the colloid is called dc, and that's the equilibrium one, although I haven't put any value for that, so you can say that's the effective d, whatever that is. Of the solute, of the chemical, yes. Yes, so C for colloid, not chemical. C for colloid, and normal D is for chemical. Okay? Good, so basically then the story will be that you should picture in your mind these molecules that are wobbly, they fluctuate, and you know what's the probability distribution of finding a given molecule in any given internal state. But if the interaction is strong enough, the attraction as compared to thermal fluctuation, which is dc, then basically they stay in touch, almost at contact, and they propel with this center of mass velocity, which will be a function of how far away from each other they will be at any instant of time. So if you want to calculate the fluctuations, for example, of the propulsion velocity of the molecule, you can relate it to the fluctuations of the internal vibrational mode of the molecule. And that will be a new feature of these molecules, which we don't have at equilibrium. Eric.
Yeah, I just wanted to follow up with his question earlier about the probability distribution. So it looks like the first term is entering in as a potential that looks just like the Coulombic potential.
Exactly, yeah.
But it's not a potential. And so to what extent can you get away with acting? Here it seems in terms of the probability distribution, it's behaving just like the potential, but in order to get the velocity, you can't just differentiate it.
No. So, I mean, that question can already be asked here. So what I have here is a gradient with respect to A of the concentration as it's felt at the position A times the mobility with the minus sign. So you can say C looks like a potential, which is the concentration. However, it's not quite, because what you get is basically the reason a potential description is going to break down is exactly because of this, because you have these, so to get the velocity for a particle you need to multiply it by the right charge, and that charge is different from the other way around, which is mu b times a. So if you want, you have this construction multiplying something that looks like a potential, because I'm looking at phoretic phenomena. If I looked at other types of non-equilibrium processes with action-reaction symmetry breaking, maybe I would not even have the gradient structure. But we happen to have the gradient structure because of that. Okay. Good. So we know how AB molecule works. Let's look at the other ones, more complicated ones. In the simulation, you saw the AB2 molecule, which had a structure like that. And the question is, if we work our way through this kind of calculation, can we say something about the structure of this molecule? So not just the internal distance, which was the only internal degree of freedom that we had here, and it didn't seem to have any structure, but these orientations, which will start to become important when the shape of the molecule becomes more complex. So let's take some time and do this calculation for this molecule. So I want to see, basically answer this question. Can I design the configurations of active molecules? So we know that molecules, when they get more and more complicated, they will basically start to have preferred configurations. This is mostly because of the orientational nature of covalent bonding and the fact that switching between two orientationally preferred bonding angles is typically very costly. So there are large barriers that KT cannot easily overcome, and then you start having these molecules with very, very distinct structures. So the question is, can we have an active equivalent of that and start putting together something like a periodic table and bonding rules and start making molecules of different complicated shapes, which we can predict or configure in advance as we want. Okay, so for this one, AB2, let's look at basically the equations of motion. So we have the same type of expression. I'll just write down what happens when they come in contact. So I'm basically ignoring the thermal fluctuations of the internal degrees of freedom and assuming that the attractions are strong enough. So I've chosen alphas and mu's and DC's such that essentially they will stay in contact most of the time. And I'm asking the question, what is the stable configuration of this molecule? So when they are in contact, essentially there'll be three expressions I can write for the velocities. I can write for the translational velocity of the A particle, mu A alpha B over D times N1. So I'm setting the distance equal to the radius. So essentially that capital R squared over little r squared is now gone. I don't need to worry about r anymore. This is essentially the translational velocity coming from B particle number 1. Then I have a similar contribution from B2. And let me call this equilibrium contribution V equilibrium. So essentially, I will have two units of V equilibrium in this configuration, one coming from B1 and one coming from B2, so along the two preferred orientations. The equilibrium one now is if you want, is something like a constraint or a Lagrange multiplier, because I'm assuming that they are in contact, so I will enforce this condition, geometric condition, that they will be at contact all the time, and I will use that to extract what V equilibrium needs to be, and then I will put it back to calculate the velocities and so on. So velocity of particle B1 will be minus mu B A alpha over D N1 minus V equilibrium N1. This is basically the reciprocal of these two terms. And then I'll have an interaction between the B particles. And that will depend on this angle phi, which I'm assuming by symmetry is the only one I need to worry about. So I constrain myself to symmetric configurations of this molecule, and I basically aim to write down an equation for phi and see what can be found. Then I'll have V of B2, again, same structure. And the B interaction is exactly the same with the opposite sign. Okay, so far it's clear? Right, now I need to enforce the condition that there will not be basically particles penetrating each other. So this can be written as a constraint. In fact, two of them. So the relative velocity between A and B, well, either of them, times the normal vector will be 0. And that means the relative motion can only happen in the axial direction of these two B particles. When I incorporate that, so I do this minus that times N1, and I solve for it, I basically get an equation for the equilibrium V, and that will be as follows. I can leave this to you as an exercise to derive, but I'll give you the answer because I need it. So this is the equilibrium. I can put it back here and basically use it to calculate an expression for the time derivative of this angle phi. Essentially, I will define it as follows. So that will be the velocity in the tangential direction will be defined as an I cross VBI minus VA dot Z hat. So you just calculate the transverse velocity, and that will give you phi dot. And here's how it looks. So the questions about the derivation itself. So you will work out the details, but the general procedure. Okay. Yes. Yes. So we basically reduce the U potential into a constraint that will make sure they will not penetrate. And literally, we use this geometric constraint to work out this. It's basically what you do in Lagrangian mechanics. You do a constraint and work out the corresponding contact forces that will enforce those. Yes. Yes. So at this stage, we didn't really talk about rotation of the spheres. Rotation is not included, and there is no contact friction between them. You can add all those if you want. Okay, so this looks like a dynamical equation. So Erwin told us a lot about dynamical systems and how to deal with them. Luckily, because we're in 1D, any dynamical equation can be thought of as some sort of coming as having come from a generalized potential, and then you can think about the minima of that potential landscape, or you can just use the expression for the velocity and look for bifurcations and see if they exist. So here I will need to plot phi dot versus phi. So this function on the right hand side, let's call it f of phi, and when you plot that, essentially you will look for the stability of the solution. So it turns out that there are three different classes depending on the parameters. So the first class of solutions will correspond to the case when the parameters satisfy this condition. So mu A over mu B minus alpha A over alpha B is less than 3/8. In this case, the stable fixed point phi equals 0 will basically explain the behavior of the system. So essentially, the AB molecule in this parameter range will always be a linear molecule, and that means there's no symmetry breaking. There's catalytic activity, but no propulsion or anything like that. Then when this combination becomes equal to 3/8, there's a bifurcation. Still phi equals 0 is stable, marginally stable, and then when mu A over mu B minus alpha A over alpha B is bigger than 3/8, then phi equals 0 fixed point, which still exists, becomes unstable, and there'll be a new fixed point phi equals phi S, which will become stable now, and you can calculate this phi S. So it's basically solution to this equation, and you can now expect to see a molecule which is bent at a chosen angle of phi S, and when there are not that much thermal fluctuations, it will basically keep this configuration, and as a result of the new found asymmetry, it will propel in this direction with the self-propulsion velocity, which you can calculate using basically the y component of the center of mass velocity, which you can do by algebraically combining these, and the self-propulsion velocity will be controlled by phi S, which means will be controlled by your parameters mu A and mu B and alpha A and alpha B. So this is a very interesting example because basically it tells us that by controlling surface chemistry, that is mu, so let's say how you put how you treat the surface of these colloids. You can put polymer coatings, you can put metal coating of different thicknesses, and so on. You will be able to go through the phase diagram and induce bifurcations like this, or by changing the catalytic activity, let's say alpha, the way the rate at which it catalyzes the fuel which is available, and switch between these configurations. Let's say going from an inert condition to a condition where translational symmetry, axial symmetries, one of the symmetries is broken, not all of it, and because of that symmetry breaking, you now have self-repulsion in the system. Are there any questions about this particular aspect of the calculation? Yes.
First one is, so with this constraint about no penetration, that also prevents the thing from just falling apart, right? If maybe the
Yes.
repulsion was too strong, you might imagine the whole thing could fall apart.
Yes, so essentially this is a simplified version of the calculation I did a little bit earlier, where essentially I allowed for internal fluctuations, and the statistical picture was that they will stay close to one another, but they are not constrained to do that. I did this using the constraint because I wanted the one parameter equation to solve and to derive this bifurcation using analytical calculation. But now,
Some other separate criteria for stability, and then given that it...
So when you will have additional degrees of freedom, you'll have a higher dimensional space, and my guess is you will still be able to see basically slow manifold type behavior in the angular direction, and somehow average over the degree of freedom which is internal in terms of the radial direction. Maybe you need to work a little bit harder, but it should be possible to do that. But this is just for the demonstration.
And maybe another question, maybe in the same spirit. So, so one idealization you need to make it easily tractable is that the concentration fields weren't perturbed in the near field. Right?
Yes.
And do you have a sense how much that would change the qualitative?
Qualitative behavior, I don't expect it to change that much, because basically higher multiples, when there are lower multiples available, as a rule of thumb, they always behave the same way. They will correct things, but they will always behave. They don't. So a higher multiple in the presence of a lower multiple can very rarely change the trend. For example, if it's attractive, turn it repulsive, or something like that. Yeah. Okay. So basically, then we can do this with in different cases, and as I said, we can start to learn rules by which we can design different types of molecules. So essentially, we can categorize them based on the symmetry that we will obtain. Then, like the list that you have here, so these four all have axial symmetry, which means that they will all have propulsion in the direction of axial symmetry. So these will be molecules with translational propulsion or intrinsic translational propulsion. Then you can get molecules like these. These actually don't have an appreciable axial symmetry, in the sense that the propulsion velocity will be there, but not really a very large value. But then there will be, because of the asymmetry that you see in the planar structure, there'll be a very strong rotation, spontaneous rotation or spin. So you will have molecules that will spin intrinsically when they form. And these are not random snapshots of a simulation. They are basically stationary states that will define the configuration, preferred configuration of these active molecules. Then you can also have, like we saw in the case of AB2, these inert molecules. They have the catalytic activity, they have the non-equilibrium activity, but only in the form of generating chemical fluxes, but not mechanical fluxes in the form of velocities or angular velocities and so on. So if you think about it, this is a very powerful toolbox, because it allows us to design these Lego building blocks, so these catalytic colloids, and then change their properties and decide what form of molecule they will form when you let them free in the solution because of their non-equilibrium activity. So you will decide their three-dimensional structure based on the parameters that they have. And then once they have the three-dimensional structure, they will have some function. They will have a non-equilibrium function. For example, they'll have translational propulsion, spin, and other things that will come later. So you will basically start to see the sort of paradigm that we have with proteins and enzymes. Essentially, you design the amino acid sequence by reading a code, and then that unique code will give you a unique three-dimensional structure when the protein is folded, and then that will give the protein a unique function. And if we can do that with colloids, when we drive them away from equilibrium, obviously this will be a very rough world, so it looks more like Lego than the smooth structural features that you see on proteins, but nevertheless the paradigm is the same. And therefore I think it's a very exciting possibility. Okay, what else can we do with these colloids? We can create bistability. For example, the molecule AB3 happens to have two isomers that are both stable under some conditions in the parameter space. So here you can see that there are other conditions where only one of them is stable. But in this particular range, you have the stable fixed points to do with the structure that we call T isomer. And because of the T shape, it's asymmetric and it propels. And then when it goes to the Y isomer, it's fully symmetric and it doesn't propel. And because it does that using a random thermal fluctuation, it basically gives you this run and tumble behavior, which is something that you see in bacteria, for example, in E. coli. But E. coli does this very naturally because it lives in the world of a U1 gauge theory. So it has a motor which only rotates, so there's only one thing that it can do, either rotate clockwise or counterclockwise, and there's only one way that it can make the transition, by switching, and the switching has to be discrete, and because of that it has to jump from one condition to another. But these colloids can have any configuration. They choose to have these discrete states and switch between them. So I think it's a little bit more non-trivial why we can see run and tumble behavior for the AB3 molecules. We can also see spontaneous oscillation when we are a little bit more patient with slightly larger molecules. So this active croissant, if you want, is appropriate name here, is basically forming spontaneously in front of your eyes, and then we will see that it can undergo a bifurcation and pick up a frequency and basically oscillate without propulsion. So here you can see how the speed of the simulation goes. Sometimes it's slow so that you pay attention, sometimes it's fast. This has gone it's hiding my molecule, this figure. You have to watch it again. Anyway, the last event is recruiting that single B, which will render the molecule asymmetric again, and then it will not propel anymore, but it will start to oscillate. So as you notice, the bigger this wedge-shaped molecule gets, the slower it becomes after it passes a sort of halfway configuration on its way to asymmetry, to symmetry. Okay, this is another one very quickly showing you how something like a, well, I won't tell you what it is, it forms. So it looks like a sperm, and what a sperm really is a self-organized structure made of protein elements that undergo a bifurcation, which is asymmetric, and it has a beating tail, and because of the asymmetry and the beating tail and coupling to hydrodynamics, it swims, and it carries a cargo, which is the DNA at the tip, and this is basically doing the same thing, but without really forcing it. It found its way itself. Okay, so very quickly, I want to show you some other types of self-organization you can get for spherical apolar colloids. This one is done in the context of thermophoresis, and as I said, basically there's complete analogy between different kind of phoretic mechanisms. So the idea is that you have these colloids, and then you shine light from one direction, and you want to see if by shining light on colloids you can get them to organize themselves and somehow create like a comet structure or swarm together. One thing which is very interesting is that they self-organize into a structure of a given finite size. So you always see these introductory slides when people talk about active matter. They show you videos of a flocks of birds that have a very distinct finite size, and they always fail to explain what it is by the end of their talk. So you have never seen a flock or flocking transition which actually picks up a finite size. It always spans the space from one direction. To my knowledge, this is the only example of a system that selects its own size, and it does so because of the peculiar long-range, well, Coulomb-like long-range or gravitational interaction that I explained. This is the top view that you can see, and you can control this size by changing the driving force, which is the intensity of light here. These colloids that are red, they receive light. The ones that are blue, they won't receive light, and that effect is taken into consideration in the simulation. And there are basically circulation lines when you average the trajectories, because single particles move faster than particles that are in the swarm, but this swarm is highly attractive the way we have chosen the alpha and mu parameters when it gets hot. So the idea is light is turned into thermal energy, and that thermal energy is creating a gradient which is basically giving you this structure. You can look at various kinds of quantities. For example, how the size depends on the intensity of light in the lateral direction, how the velocity of the swarm depends on that, and so on. You can do particle tracking and follow individual particles and see how basically the mean squared fluctuations currently being masked by the video behave in the perpendicular and transverse direction. You can increase the intensity of light and get lateral oscillations in the comet, as well as breakup events or fission events like that, because essentially the attraction between the different components becomes unable to cope with the extra drive that we have. And then there are also these lateral waves that propagate along the comet. So it's an excitable medium. You can see here the traces in the chymograph that that we found here. Right. So this was very briefly the last thing I wanted to say about about apolar particles. Are there any questions? No, it's not. Yeah, it's not the momentum, it's the shadow. So so light comes from here, and then you have a colloid which receives the light, and then you have another colloid which only receives partially light, and then the Spherical coefficient is negative, so this one will feel a component towards this direction, because that's how the gradient of temperature will be, and there's a component in that direction which is created by this active heat of a source of heat, and then this will generate the tendency. Okay, good. So I might just mention that something we're doing right now with these AB mixtures is look at higher density configurations and other parts of the parameter space where you don't see the molecules but you see phase separation, and they are showing very interesting behavior. For example, phase separation that shows two different types of dense phase, basically. Hopefully there'll be a preprint on that appearing on the archive maybe next week or the week after, and you can look it up if you're interested. So this is my 5-minute break. Okay, so now we want to talk about collective behavior with polar active particles, so Janus particles, which, as we saw, are going to be a lot more complicated for a few reasons. So this is the system I want to look at, a solution, a collection of these Janus particles, each of them being self-propelled by creating this catalytic co-moving cloud. And the degrees of freedom that I have will be position and orientation for each one of them. Then you notice that basically each particle will generate a gradient by being source or sink of chemicals, and then the other particles will respond to the gradient phoretically. So the center of mass response, the translational response, will be to move away from that source or move towards it, depending on the mu values. And then there will be also the possibility of rotation, because these Janus particles are asymmetric, so they will have an alpha 1, the first moment in the Legendre expansion, which means if I have a gradient here of the chemical generated by all these guys, this particle will also rotate. So there will be an angular velocity as well. And then you can start to see how things can get complicated. So I have two colloids. What is the interaction between them? Well, they can attract each other from the translational point of view, or they can repel each other. They can create a gradient which will lead to alignment. The alignment could be both aligning towards each other. So you could have a situation where they align towards each other, swim towards each other, and attract each other. Okay, that's a no-brainer. They will collapse and collide, and that's it. You can create a situation where they will attract each other, but they will align opposite to the gradients. So now they want to swim away from each other while dragging each other towards inwards. So basically that means you will have opposing tendencies, and you need to work out what the balance will be and what the outcome will be. And you can flip the signs and think about all the other possibilities. So repelling each other while swimming away from each other, that's a no-brainer. They will go away and give you a dilute system. Swimming away from each other, swimming towards each other but repelling each other, that could also be a conflicting situation, and so on. So we want to study all that and understand all that, and as always we build systematically the description. So I want to start from Langevin equations. So each particle will have a velocity which will be made of different components. I don't want to think about it right now. And there will be a noise component for the translation. I choose to write the strength of noise explicitly, so square root of 2d will control the strength of noise, and then psi is just the Gaussian white noise of unique strength and vanishing average. Confusingly, this is my dc now, and it looks like d, so there won't be any explicit chemical d for a while. So I hope this will be okay, or we can just carry through a c, but we can just drop it. Then I need to write the equation for n. Also my hats will drop off because I have n, and n is obviously a unit vector, so we don't need to remind ourselves. So let's say I have a collection of, say, capital N colloids, each of which having a position and an orientation satisfying this set of Langevin equations. There'll be a translational, a drift part, and then a stochastic part. And I can use this to derive an equation for the probability distribution of this system. So I want to look at the probability of finding a particle at position r with orientation n at time t. And that is the average of the sum of delta functions checking whether any particle at that time is at position R, and whether any of them that are there will happen to have orientation n at that time. If these two conditions are checked, then this will count towards the probability. Otherwise, it won't. Okay? I'd like to define a rotational gradient operator. Many of you have seen this. It's basically an angular momentum operator without an I. And without an H bar. Right? So if you think of this as that, essentially when R is sitting on the surface of a sphere, all you care about is moving on the surface, which basically means angular changes. So this gradient operator is essentially an angular momentum operator. And it's helpful because from quantum mechanics you will remember, so essentially in units where H bar is 1, so you will remember the algebra for various components of angular momentum and the representations and so on, and you can use all that when you're dealing with powers of the gradient. It's very helpful. Okay, for example, when this operator acts on n, it gives you minus epsilon alpha beta gamma n gamma. That's basically because n itself is a spin 1 representation of the rotation group, of the SO3 group, and essentially you get the coefficients that define your algebra. When R squared acts on n beta, you get minus 2 times n beta. This is L times L plus 1 in the algebra of angular momentum. So L equals 1 gives you 2. And the minus sign is because of this I, right? So it's fairly simple if you remember quantum mechanics. I'll leave it there. I can define fluxes, so translational fluxes. Actually, I can drop the explicit mention of time dependence, minus d gradient of p. This is the translational flux. And I can define the rotational flux or the angular flux. And then I can write down the Fokker-Planck equation. That is simply the conservation of all the fluxes. So it's a probability conservation, and it takes into account both degrees of freedom. And then you can now specify that you're interested in this particular problem, which is a phoretic system that is self-propelled, and it generates the gradients and so on. And that is essentially done by using these definitions. So you can say I have a self-propulsion, and then I have a response to some field, psi. I call it psi, not C or T or any of the known thermodynamic potentials, just to keep it generic, although this looks like zeta potential in an electrostatic field, but let's just imagine it's a generic field. And then for the angular velocity, you will have an alignment term. This is what you derived as a homework. So essentially we can say this will be typically a concentration when we're dealing with diffuse geophoresis. It's the electrostatic potential when we are dealing with electrophoresis. Its temperature when we're dealing with thermophoresis. Okay. So when I combine the expressions I had for the fluxes that I have them here with these velocities and put them in this expression, I get the following Fokker-Planck equation. I have to mention here that this is a simplified version of the story, so I'm not taking into account, for example, the reaction scheme that will take some substrate molecule from the solution and produce some product molecules. So there will be two species that I need to worry about. I'm not taking into account the explicit way that V naught is generated, and it will be a function of the ambient concentration, which basically will be the field psi here. I'll just treat it as a constant. All of those things will come out later. So for now, let's just build the simplest version of this theory, which will have the elements that you need. So you need propulsion, you need generation of this field, and then you need the response to that, which is in terms of translational response and alignment response. And let's see that we can build this and all the elements are there, and then I will go back one more time using slides this time and give you the full picture. Okay. So here is the translational drift. Here is the diffusive term for translation. and then the rotational part will have the alignment term and the rotational diffusion term. So this is the equation I want to solve. Yes? So two things about that question, important question. One is I haven't told you yet what psi is and how it's generated. That will be another equation that I need to write. Secondly, here I'm ignoring hydrodynamics. That's an important point, and you can notice this because I don't have the mobility factors that I had when I started the lecture. So if I want to have hydrodynamics, I can simply put in those mobility factors here. Again, this is version 101 of the theory. You can always dress it up with more complications. So it's the list of essential ingredients that will give you that phenomenology, and then there will be additional realistic things that we need to add and ask the question, do they change the phenomenology or do they just change the values a little bit? Okay, so this equation should worry you, especially I imagine Mike Shelley had equations similar to this, and maybe he spent a lot of time trying to explain to you what they mean or how you can extract things out of that. So this is basically an equation which couples, so the culprit here, the troublemaker is this guy, is an orientational variable which sits in the translational part of the equation, right? And that's the problem, because in order to solve, if I didn't have this V naught here, I could just say, oh yes, this is just the translational part. I deal with it separately. That's just the orientation part. I deal with it separately, and then I combine them. And that's how we do equilibrium dynamics of rods, let's say, that align to external fields and shear and electric field and this and that. It's not easy, you know. Doyen Edwards still is a big book, but nevertheless, you can conceptually be comfortable with the calculations. Here it's a different story, because anything you want to do, you need to mix the 2 degrees of freedom. Okay? So how do we do that? We use moment expansion. And what moment expansion does is basically it will generate moments of the end part of the probability distribution. So it's like doing multiple expansion. Instead of, in fact, it is equivalent to multiple expansion. Instead of dealing with the full dependence on n, you basically deal with the averages of different powers of that. So the first moment, the 0th moment is just average of that over n. Let me actually write down what I'm saying so that we will save some time. So if I integrate over the orientational degree of freedom, I will get essentially the density. If I multiply this by n and then integrate, I will get the polarization. If I multiply it by 2n factors and subtract the trace, because the trace is in fact nothing but the density. This is basically the dimension. I'll get the nematic order parameter, or you can call it the nematicity. And the list goes on. You can multiply it by any power of n and generate that moment and say you're interested in knowing how that particular moment behaves. How does that help us? Well, we have the equation, so we can generate the moments directly on the equation. So I can say I take the equation itself and just integrate it over n and see what happens. And I think we have enough time to do that. So if we call this equation this symbol, if I integrate this equation over n, I'll get the following expression. The first one will give me just density. The self-propulsion term will give me V0 times divergence of the polarization. That's fairly clear from the expression itself. Then I will have a term that basically includes the Phoretic drift. Then the orientation, so the diffusive part will again give me density, and the orientation part will integrate to 0 because it's a complete divergence. So this is the equation that I will get for the 0th moment. As you can see, it's a very nice equation. It looks like a drift diffusion equation for the density. It has a divergence of a deterministic drift velocity which depends on some external potential with the mobility mu, and it has the diffusion term. However, it also has a divergence of a polarization, which is a higher moment. It's the first moment of the distribution. So that's, without this, I'm home safe. I can solve this equation and study the outcome of the effect of psi. But with this term, I need to do something else. And that something else we will do tomorrow. We will look at the first moment of the equation and then see what we can do with it. Okay?